Hi, I'm Jennifer Novotny and I'm a graduate student at Cornell University.
In the last 4 years in the DICTAB research group, I've been focusing on a type of material known as porous organic polymers. So to understand my research, we're going to have to break it down into 3 parts.
The best place to start is to talk about polymers. Polymers are large molecules that are built up of many smaller units that we call monomers. The monomers are then bonded together to make up many of the materials we see in the world around us, including plastics, rubber, and vinyl. While most polymers are strong, they can also be flexible, free-flowing, or even sticky. By changing the length of the polymer or changing the atomic composition, we can fine-tune these physical properties for a variety of purposes.
To help visualize what a polymer is, I've enlisted the help of my friends. We're going to make a human polymer where each person represents a monomer. When monomers hold hands together, they make a covalent bond, which means that they're sharing electrons. That means now that these 2 monomers are linked together and can continue to grow to build a polymer. We can visualize a type of polymerization known as chain growth polymerization with a game of tag. The initiator starts the polymerization and the monomers add on one by one until we have our final polymer.
Now that we've learned a little bit more about polymers, the second part is organic. Organic in this context doesn't mean grown without pesticides. Instead, in chemistry, organic means that the polymer contains carbon. The periodic table of the elements lists all of the elements that are known to man. The polymers I make contain carbon, which makes them organic, and they also contain oxygen and hydrogen and sometimes boron. Now the last part is porous. The person polymer we built earlier is an example of a linear polymer, which means that there's no branching. The polymers I make are 2- and 3-dimensional polymers, so instead of having my friends try to climb on top of each other, we can use another analogy from the playground.
The best way to think about what a porous organic polymer looks like is to think about a jungle gym. The polymer gives it shape and rigidity, but there's still a lot of free space inside.
The polymers I make have a surface area of around 2,500 meters squared per gram. So to help visualize, that's about the size of 1.5 hockey rinks folded into a single gram of material. Now that's big. My research group is studying new ways to make these porous organic polymers, as well as finding ways to utilize all of this free space for new applications. I have studied using porous organic polymers to detect TNT vapor. The high surface area of the polymer allows the TNT to diffuse through the pores more easily. This means that the TNT is able to interact with more of the polymer. My research group has also studied using these porous organic polymers for energy storage devices. The pores of the polymer allow for more charge to be stored compared to a flat surface. You could then envision a higher surface area material being able to store more charge. These devices could be integrated into cars, which could then help power our move away from fossil fuels. By studying porous organic polymers, my research group aims to solve many of the problems that are facing our society today.